stimulus. Urgency is determined by a parameter V naught and is identical across all stop signal delays. The discrimination component is absent at zero SSD trials, as the choice stimulus is not presented yet, but increases linearly with stop signal delay at a rate determined by parameter G until it reaches the level of regular go trials without a stop signal. Therefore, the match and mismatch evidence accumulation rates are identical on zero stop signal trials and gradually move apart from each other at longer delays until they become equal to go trial levels. We actually explored exponential power and logistic versions of the model, but we found that simple linear growth provided a parsimonious and sufficiently accurate description of the stop signal delay related trends in the data. So these figures show the fit of the model to a random representative subset of, I think, about 900 participants. The bottom panel shows the fit of the misspecified hybrid model that assumed context independence. And you can see this is the accuracy rate, which you can see at zero SSDs, it starts at 0.5 because the stop signal completely matches the choice stimulus. And then it raises to an asymptotic level. And you can see that the misspecified model that assumes context independence clearly fails to account for the steep increase in accuracy of the function of stop signal delay. The top panel shows the fit of the hybrid model that does not assume context independence. So with only two additional parameters, the urgency and the perceptual growth rate parameter, the model can adequately capture the accuracy data, as we can see. And the same was true for the increase in the probability of responding to stop signal trials as a function of stop signal delay. So again, this is a prediction of the race model, and we can account for that very nicely. And also the increase in signal response RTs as a function of stop signal delay. So the model seems to account for the observed data very well. And as you can imagine, we were very happy with this result because with this model, we can now compute valid and reliable stop signal RTs even in the face of the serious validation of context independence. And we have arrived to my last section about stopping in the real world. So successful real-world interactions, of course, do not only involve withholding responses as in the stop signal paradigm or in RE tasks. When you stop the overtaking maneuver in response to the ambulance siren, you don't just let go of your steering wheel and sit back, right? You may steer in the other direction or hit the brake to avoid a collision with the car right in front of you. Also, stop signals in the real world are not always as clear as a loud beep or a red box on the computer screen. Traffic lights may be obscured by rain or fog, and you only often need to make decisions about which stop signals are relevant for you and which you can safely ignore. So an ambulance coming right behind you in your lane is important. An ambulance coming 4 lanes down the road is maybe less important for you. As these examples illustrate, stopping in the real world often requires complex decision sequences and behaviors. And in the final few minutes of this talk, I would like to give you a few examples of some preliminary work in my lab that addresses more complex form of stopping. In the past year or so, we have started to experiment with generalizing our parametric race models to other popular response condition types, such as a stop change and selected stopping paradigms. So as opposed to the standard stop signal paradigms, the stop change paradigm doesn't only involve the withholding of the go response, but also subsequent overt response to the stop signal. So for instance, in this example, the stop signal, the red box, would indicate that you should stop your manual response to the arrow and then quickly press a foot pedal. In selective stopping, again, a paradigm that we're interested in now, you're essentially presented with 2 types of stop signals: regular stop signals and ignore signals. The regular stop signal, the red box, indicates that you should withhold your go response, whereas the ignore signal, the yellow box, would indicate that you should continue with responding. So you have to make a choice, a decision about the identity of the stop signal. This is called stimulus selective stopping. There are various variants of this task, such as motor selective stopping, for example, where you're only required to stop, say, your left-hand responses on stop trials, but not your right-hand responses. And also, so these paradigms come in many different flavors. But regardless of the exact implementation, there are currently no valid methods for estimating inhibitability in complex stopping paradigms. And this is largely or probably actually fully attributable to a lack of appropriate formal models. For instance, selective stopping still relies on the non-parametric standard force-based model. And even though it has been shown the resulting stop signalarity estimates are mathematically flawed due to violations of the model's assumptions, or fail to reflect the selective nature of stopping. So we are now working on parametric hybrid race models, instantiating various theoretical kinds of performance, stomp change, and selective stopping paradigms, and even in various combinations of these paradigms. And our goal is not only methodological here. Our aim is to figure out whether these more complex forms of stopping, whether these provide a better measure of implicity than inhibitability derived from the standard simple stop signal paradigm. As I mentioned before, evidence for the relationship between implicity and inhibitability is weak and inconsistent. In fact, we have shown that failure to trigger the stop process is a better predictor of impulsivity than stop signalarities. But I cannot help but wonder, what if the stop signal paradigm does not measure the type of response inhibition required in the real world? Indeed, it has been suggested that more complex types, such as selective stopping, may provide a better model of the cognitive control that characterizes our everyday lives. Currently, there is little direct empirical evidence for these claims, but I believe that our models will help answer this important question. But I'm afraid that we'll have to wait another talk. And I would like to thank you for your attention, and also thank my collaborators. Sorry, something was weird in the session. Anyhow, thank you for your attention. And also would like to thank my collaborators who work with me on these models. So yeah, I'm happy to take any questions you have.
Okay, thank you very much. That was really interesting. So you can ask questions in the Q&A. Now I think I need to say answer live to see the question of Himanshu, who is asking, is it possible to get independent measure of non-decision time for each participant and use them as fixed parameter values in drift diffusion models?
That would be nice, yes. So that is actually, so we are experimenting with two approaches. So this hybrid approach is a very straightforward statistical solution for this, but we still don't, we cannot get to the full evidence accumulation framework with this. So one approach would be indeed to get a estimate of the non-decision time of the stop rudder one way or another. We are looking at two approaches. One is a more experimental approach where we use a calibration task to get that estimate, and the other is a more neurologically inspired, neuropsychologically inspired approach where we try to use ERPs to measure the onset of evidence accumulation. These may work. I am moderately hopeful. One thing that we know already now, that this is going to be technically very challenging exercise. So we will have to need quite a long testing sessions, maybe even multiple testing sessions, and we will have to model the different sources of information simultaneously. So we are talking about huge Bayesian multivariate models. But yeah, that is definitely the way, and I really hope that we will get there eventually, because that is absolutely my goal to arrive at a full evidence accumulation framework for this program.
Okay, I have a couple of questions until new questions arrive. So something that I wasn't entirely clear was about this delta function that you mentioned, that if there is a violation of this independence assumption, it will go down. Can you explain a little bit more about that? Why is it that it goes down when there is a violation of the independence assumption?
So an independent race model, independent of the parameterization, whether it's X Gaussian, as long as they're independent finishing times, it predicts a function. It predicts this fan-shaped pattern.
Why
so the signal responder distribution should always be left to the Dora distribution. So simply we just subtract those two lines from each other, and that must result in an increasing line. So that's the only idea behind it, and that is a purely statistical prediction. Those any independent model predicts that fan shape in the two distributions. And if you translate them to delta functions, you can see that there's an increasing pattern.
Okay.
So if you can't accommodate that, that means that something is going on there, possibly context independence violation.
Okay, where people change their no-go response based on the go response. That's the lack of independence, or I missed that.
Sorry, I'm not sure I understand that question.
So what you showed in this new paradigm, the ARE, is that people behave differently in the no-go responses based on what happens in the go response.
Yes, exactly. Yeah. So something I think was going on, something during a stop trial, it's not only the rising of the bar, but something else happens, and that causes people to judge time and how the time differently. And that is a violation of the model, because the Go process should run the exact same way on Go trials and on trials where we get a stop signal. And what we see here is that the Go process actually is slower and more variable on stop trials relative to Go trials.
Okay, I see. I have more questions, but I see something from Ivan Camponogara, who asks, how does the model account for the learning rate of the subjects? I believe that at the beginning of the experiment, subjects learn when to stop the action, and their failure to stop is not due to an attentive process, but only because they have to learn the task. I was wondering if there is a way to account for learning, and if there is a plateau where task is learned and failed stop trials can be considered as trials where participants haven't paid attention to the task.
So it's a very nice question I've been wondering about. So I think there are ways to model this. So one way at this point, so we don't account for learning in these models at this point, right? What we do is run quite a lot of practice trials to get participants to a stable performance. So first we run a lot of Go trials only, the choice task. And so they learn to sort of respond quite quickly and automatically. And then we add the stop signal to the mix, and then we run again a session with that. And then we start an actual experimental session. So this is what we do now, but it would be super interesting, I think, to model how learning and how environmental influences affect people's performance. And this is in fact something that I had just received some funding for developing these types of models. So that's something that I can't tell you now if it will work out, but we are hoping to combine some reinforcement learning algorithms with governing the learning in these models.
Okay, I still have more questions, unless someone else asks something, or Shravan maybe. But I was wondering about the drift diffusion model. I understand that you have a race between the go and no go, but why do you have a race between the two goes?
So there is a component in race model. Sorry?
Yeah, wouldn't it be more parsimonious to assume that evidence for left goes against evidence for right? And then you have like a regular drift diffusion model with two boundaries and another one with only for the no go?
You could do this. So you could have a sort of the winner from the diffusion process for the Go trials race with the stop process. You could do that. But so response innovation has been traditionally modeled as a race from the starting with the work of Gordon Logan. And the race models are also, of course, very popular choice for simple choice RTs. So we have, of course, a diffusion decision model, but we also have other evidence estimation models, just like the LBA or the race involved models that pretty much do the same, but they assume a race and not a competition. But it's a matter of taste, I guess. You could, what I said, you could combine a diffusion model with an ex-Gaussian stop runner, but those two would still race against each other. So it would pick the winner of the diffusion decision model and let it race with a good process. We haven't tried that yet. I don't know if it would work better or worse, so I can tell you that, but that is certainly a possibility.
Okay, yeah, it seems that you could reduce the number of parameters if you have like one drift diffusion model that can go left or right, and then that races against something else that could be, yeah.
Yeah, you could, like, I guess it would, in each and every paradigm, it would boil down to which fits better, right? So there are cases when when we fit choice RT data with the DDM or with the LBM, we see that in this particular case, we can capture especially leading edges of the distribution better with one model or the other. And I think that would be also interesting exercise to look also into this in the stop signal data.
Okay. So unless there is, there is another question. From Himanshu, I think this will be the last one. If I have another chance to ask, I have a naive question. I am completely new to this literature. My impression is that race model inequality test is required to conclude whether data supports a race process model, of course, after the model satisfies the context invariant assumption. I was wondering whether you do race model inequality test for evaluating race models for stop signal paradigm data. And can this test be potentially applied on your hybrid model?
So what we typically do, and so there are various steps that we do, or well, you should do if you're doing the modeling properly to check this assumption. So just like for any other models, whether it be the DDM or whatever type of cognitive model, you want to know, of course, if your model describes the data well. And if you use non-parametric methods, typically what you do is what I said already. Actually, you compare mean signal response RTs with GoRTs. And if the signal response RTs are faster than GoRTs, you typically conclude that I'm good to go. This is a very low bar, right? So this is what typically happens. There are other predictions of the race model that we look at is increasing inhibition functions. So the probability of stopping should get more and more difficult as the delay increases. And this is something that we typically find. And a third check that people typically do is looking at the increase in signal response RTs as a function of stop signal delay. So that again actually comes from that prediction of the race model that the signal response RTs and the GoRT share a common lower bound. So this is what you typically do to check whether the race model holds. If you go parametric, you can of course do more. You should also check if the parametric form you assume for your RT distribution, as we do your X Gaussian, but could be something else, could be a Bible, could be just a normal maybe for the stop RTs. You also want to check that. So what we do is we use posterior predictive simulations to check if we can approximate, the model can actually predict, can produce fake data that resembles the real data. And if it can, then it is still, it doesn't mean that everything is working fine, but there are no gross violations at least. So this is how we check.
Okay, I think we ran out of time. Thank you very much, Dora.
And thank you for attention.
It was really interesting. And yeah, so we'll continue tomorrow with our summer school. So goodbye.
Thanks for the invitation. Bye.
Thank you very much, Dora. That was super interesting. Bye-bye.
Bye.